you completely forget about, that's fine. But I want to get some feedback on this. So I'm Mike Lamb, for those of you who don't know me already. I'm at James Madison University, which a lot of people have never heard of. It's kind of this large liberal arts public university in the state of Virginia in the US. And so I am in the computer science department, but lately I've been kind of moonlighting in the math department. So that's sort of the context for this stuff. And it's why I've got, the Beamer slides for you today, because I've been borrowing stuff from the math department. So we have a group of faculty here in the math department that are really good at using power series to solve ordinary differential equations. This is kind of their thing. They apply this to a lot of different problems. And I have a very, very thin grasp on the actual mathematics of all of this. But the basic idea is that you sort of create a polynomial curve that approximates the solution to an ODE at a particular point. And then you kind of take a time step and you build a new polynomial representation. So we'd already, someone else talked about, Santosh, I think, talked a little bit about polynomial approximations earlier today. So this is sort of the math things. This is about the extent of the math that I'm going to show you. But so we have an initial value ordinary differential equation. And so we basically generate numerical solutions. So we sort of assume that we can represent X this way, and then the derivative ends up looking like this. You have to massage it a little bit. And so then what you do is you take these these power series and you substitute them back into the original equation, and you find recurrence relationships for the coefficients of the polynomials. And so once you've done that process, then solving it is a very computationally efficient process, and it's mostly just doing multiplications and additions. And that works for linear ODEs, but the group here, their contribution to all of this is that they've come up with a pretty robust system for doing this for nonlinear equations using something they call auxiliary variables, and using a bunch of Cauchy products to handle all the nonlinearities. So that's sort of where they're coming at this from, and they have tons and tons of papers on the math for this. Basically, under the hood, the code algorithm boils down to this, where you just kind of have a loop for each step as you're numerically integrating the ODE. And there's this routine that calculates all these coefficients for a particular degree polynomial, and then you evaluate the polynomial, and that gives you the next point. You update the time, and you can move to the next step. And so what I guess sort of caught my eye here is that they have this degree thing, which is now a parameter to this solver. So, in a lot of solvers, the time step is a parameter, right? You can change the time step of your solver. Sometimes it's adaptive, but their degree is also parameter. And my understanding is that this is somewhat novel. A lot of the other ODE solvers kind of have the order baked in, like Runge-Kutta, and it's a little bit difficult sometimes to kind of change on the fly what polynomial order you're using. And so I thought, well, so they're already now sort of building this two-dimensional search space, right? Why don't we add floating point precision? And now we have a three-dimensional search space, which is going to be, so much more fun than just having a two-dimensional search space. So anyway, I sort of helped advise an REU last summer. I think I may have talked to some of you about that. The REU itself did not actually turn out terribly great. I'm not sure I would recommend running an REU on Zoom. You miss a whole lot of the, getting people together in a shared space and writing on a whiteboard and everything. But we had some students and they worked on some of these equations here. So these are the three main equations that they worked on over the summer. They're somewhat difficult to compute numerically. And so the progress that was made last summer is that we actually got C++ solvers written for these. I showed them how to use templates in C++, and so we parameterized everything so that we could change the data type really easily. And then the one thing that came out of this that I thought was just kind of a little minor addition that turns out to be something that a lot of people are interested in is that I actually wrote a little Java utility that lets you run the C++, the compiled C++ code, grab the output, run it through GNU plot, and generate the plot. And so one thing that we wanted to be able to do was to see how changing the order of the polynomial and the different other parameters of the ODE, how that affected the solution. And so this allowed us to do that in real time. And I'm going to show you here in a second. And so the primary contributions for the summer is that all of this happened and we ran some initial experiments. And it didn't quite sort of get wrapped up as nicely as I would have preferred that it got wrapped up. But it kind of gave us a starting point for this summer. So I'm going to now throw the program up. So here's what the little viewer looks like here. So this is what's called a van der Pol oscillator. We're looking at the solution over here on the left, and then you're looking at the phase portrait over here on the right, where we would just plot the value against its derivative. And so again, what's happening here is that this is just a little Java wrapper around a compiled C++ backend and GNU plot. And so what's cool about it is that we put in these little sliders so that you can change the value of the parameters and actually watch the solution to the system change in real time. And so it becomes sort of immediately obvious, right, as you're studying this, oh, this is a dampening factor, right, because you can see exactly what's going on. And so, you know, it's kind of cool. We can sort of change. So this changes the time step. And so what I've been sort of looking at so far, and I haven't really gotten too terribly far on this, is so what kind of happens at the low ends here? So this is the time step. So, you know, as we take larger and larger steps, we would imagine it being less and less accurate. But we can see that it's still holding up pretty well. Like you were still getting basically the same solution here, even for very large time steps. And so this is the degree of the polynomial. So right now we're at order 5. This is pretending to be a real number. It's actually an integer number. So it'll actually, the value here gets floored before it gets sent into the actual solver. But you can see that as I change the order, right, the solution changes pretty dramatically, going from like a second order to a third order to the fourth order, and then it pretty much stabilizes after that. And so what I thought was interesting was to look at sort of what happens as you start turning the precision level down. And this is also kind of an integer quantity, and it's even worse than being integers because it's only the powers of 2 right now. So we use, I have implemented single precision, double precision, quad precision, and then on the low end, I was able to get B float working. I couldn't get half precision for some reason. I need to revisit that and figure out what was going on with that. So this is using double precision, and then we can drop it down to essentially single precision. Again, these are, this is really just kind of dropping it down to the next lowest level. So that's down to single precision, and then that's down to quad precision. And that's really the only difference you can sort of see in terms of just changing the precision level. And I think that kind of speaks to the robustness of the actual solving algorithm. But what's kind of interesting, what caught my eye in playing around with this is that even at bfloat 16 level of precision, changing the time step doesn't really change the solution that much until the order gets below 4. And at that point, the solution starts to change. And you're actually, you know, basically, presumably getting the wrong answer just by changing the time step going from the 3rd order to the 4th order. And, you know, maybe that's interesting, maybe it's not, but I thought it was kind of cool that I was able to sort of discover that bit of the mathematics just by playing with these sliders, right? Like someone with very little mathematical training actually found something that could be kind of interesting from the mathematical point of view. And so I thought that was pretty neat. We can pull this back up later if folks want to actually look at it. But I think that we're pretty much done with my time slot for the presentation. So I'll just mention that I have, so one other demo that I can show if people are interested in it is a much more complicated thing that we're working on this summer. So this is for a full 6 degrees Newtonian physics simulation. So I can bring that up later if folks want to see that. But just to wrap this up, this is what we're sort of thinking about it for future work. So being able to see multiple plots, so that's already done. So I can show you that if you'd like to see that. I'd like to try to transition this to some sort of native Java graphing library so that we can eliminate the GNU plot dependency and have a little bit more flexibility in how we render stuff, applying it to more recent models and just running more experiments. I would love to have some students work on this and just kind of experiment with it. So acknowledgements, supported by grants. And here's the repository if you'd like to fool around with it. It's a little bit, as all these tools we were just talking, it's a little bit rough at this point because it's sort of in progress. And I have a student this summer who's actually working on improving the viewer itself and rewriting it and making it better. But just feel free to ping me via email, or I'm also in the Slack if you're interested in using this.
Very cool. Very cool. I love this idea because I've experienced exactly the same thing before, of messing around with sliders to control parameters and watching what happens in real time, and then learning things about the underlying math without ever having like solved for it. And it is very, there's like these very interesting sort of cases that you'll just run into where things become stable or become unstable. And you, like, you know, I'm an experimentalist. The way I will do this is like, oh, just, you know, try it, see if it makes a Pareto frontier or not. If it doesn't make a Pareto frontier, it was unstable. You did something wrong. You know, this is like a, so this idea resonates with me. And it is like, and this is the perfect question. I'll actually talk about this in my talk, where you have this thing where the precision interacts with like the order and the time step. And like optimizing all of those at the same time is super, super, super interesting, because they all interdepend. And it's like the relationships are, you know, sometimes it's kind of boring. It's like, oh, I need enough precision, but finding the edge is very cool. So.
Well, and so, you know, there's a million little visualizations like this online for education and everything. And I guess sort of the one potential contribution here is that, you know, this is not, you know, interpreting, you know, something in Python or in JavaScript or whatever, right? This is running a compiled, optimized C++ backend. And so those particular examples that I was showing you before aren't all that crazy, but this is, this one here is something that we've been working on recently. And this is like 1,000, 2,000 lines of C++ solving, you know, about 20 different equations, and, you know, in generating 4 different plots. And, you know, it's slower. You can see that it's updating more slowly as I'm moving it, but it's still updating in what I would consider real time. And this is apparently something that's entirely new to the scientists working on this.
This is super cool stuff. I think in the interest of time, we're gonna keep pushing ahead. But Mike, also one thing that might be worth looking at is Theodore Amsgaard's universal library for having a bunch of different numerics provided, and that's all C++.
Yeah. I was going to say that as well, although of course you start running into the problem that the performance is going to tank if you're not using the built-in stuff. So there, yeah, I mean, there's interesting trade-offs, but yeah, for sure. It's one of the things is like, I would love to see the continuous, you know, how many bits, because I think there's a lot of interesting behavior you would see, but